everyone, my name is Zhe Wang. I'm from Rutgers University. In this video, I'm going to present my solution for the BitTiger micro project, Mini-Cassandra. Cassandra is an open source project which is initially developed by Facebook, and it is a NoSQL distributed database, and it uses the underlying concept of DHT, distributed hash table. Before we get into how to implement the mini version of Cassandra, let's talk about why do we need that. So the most initial idea of building database, just like building all the other applications that is using the centralized structure, meaning there will be a logical centralized machine or logically single machine which stores all the data for certain applications or system. And all the users or clients who wants the data, they go to this single one place to ask for it, and this single database will return the result to the users. Well, due to the limitation of single one machine, and this machine becomes the bottleneck in very quick manner. So therefore, people tends to introduce the decentralized or distributed structure to build the database. So then it became something like this, right? So basically, people have to do the data sharding to distribute the data. And this is just an example, right? So but this is a very classic scenario that people distribute the data in terms of different module of the system, or we can say due to different schema of the database, right? But you may immediately have the concern that, well, the data is not evenly distributed, right? And also, for example, in this case, the database that's storing the sales data might be growing tremendously, while the other two parts remains relatively stable volume of the data. And and maybe the data takes only part of the the database, and the server is kind of wasted, while this one is struggling with the huge volume of requests, right? So people introduce another way of distributing data, or to do the data sharding. That is, to have a way, whether we can use the modulo or use the hash function, to distribute the data based on certain, let's say, primary key, right? So in this case, right, we have two servers, so we just do mod 2, right? And based on its key, let's use the example of data 0, data 1, data 2, something like that, right? So when you do the modulo, then as you can see, right? Data 0, data 2, data 4, because they are even numbers, they goes into this database 0, and data 1, 2, 3, 5, they are odd numbers, so they go into this database 1. So in this way, we can pretty much balance the workload of database, right? So that's a relatively better solution. However, you may think about some other limitations, right? The limitation is how to scale up, right? Let's say you have so much data, so 2 database server cannot handle that. So you need to introduce another one. Now what? Who should we move from database 0 or 1 to 2? We have to do the recalculation, right? Or we should say rehashing, right? That is, now instead of mod 2, we just have to do the modulo of 3, right? So for data 0, it will be still in database 0, but for data 2, it will go to database 2. And for for data 4, it goes to database 1, right? Because it's 4 mod 3 is 1. And then data 1 remains in 1, data 3 goes to database 0, and data 5 finally goes to database 2. Right. So this is scaling up. There could be another scenario of, well, let's say what if some server died and you cannot, or some server needs to be maintained, right? Or do the maintenance work, or has to use for other purpose. You have to get rid of one server, but you want to move those data to other place. Now you have to do another rehashing, right? So it's painful when you just add new servers or remove servers, right? Then people come up with I would say, this is for the 2 servers, right? Then people come up with a even better way. That's what is called consistent hashing. And the people consider data as a virtual concept of key value pairs, meaning each set of data, they have certain key, right? Like say primary key or ID or something like that. And they use a hash function that map those key into a, into a large number. In this example, is from 0 to 15, but in real life is from 0 to the 2 to the power of 32 minus 1, something like that, right? So it's a large space. And as you can see, this 4 blue dot, they are the servers we are talking about. So due to those hash function, they got certain number. And for those data, they also have key value pairs. So those data can also be mapped into this ring. Alright? So, and now is the question, how do we distribute those data? So the rule of consistent hashing is, for every node, just takes care of the data that has the key of the server or the database and before it. Alright, so in this example, 8 is going to take care of data 4, data 5, data 6, data 7, and data 8. Server or database 10 is going to take care of the data 9 and 10. Oh, sorry. And server 14 is going to take care of the data from 11 to 14, and server 3 is going to take care of the data from 15 to 3. Alright, got that? So those four kind of distribute the certain, how to say, range of data, right? So then you may ask, well, why this is better than the previous one, right? Previous one is also one server takes care of certain range of data, right? The reason this is better is, let's see what happens when there's one more server. Okay. Now let's see, the 6 is newly joined server. By the rule, 6 is going to taking care of 4, 5, and 6, right? And 8 in this case is going to taking care of 7 and 8. But remember who is taking care of 4, 5, and 6 before 6 is joined? It's 8. So before 6 joined, 8 has 4, 5, 6. After 6 joined, all you need to do is to let 8 give 4, 5, and 6 to 6, to server or database 6. And all the rest of data and the server on this ring, they don't have to do anything. Only the one who is the successor of this newly joined node. Okay, so this eliminates a huge amount of data movement, right? So that's one improvement. However, consistent hashing also have its, well, we don't want to say it's limitation, but it's something that we can improve. That is, let's say if you are node 3, when people ask you for data 0, well, you can return it, right? Because actually you are taking care of that. So actually data 0 is stored at 3. But what if people ask 3 about, let's say, data 11? What should you do? Well, because you are 3, so you don't have 11, and you do not know who is holding this 11, right? Because actually you don't know whether there's node 11 or server 11. So what you have to do is you just, kind of ask around. In this case, you can ask 6 to say, do you have 11? 6 said no. Then you have to ask 8. 8 said no. You have to ask 10. 10 said no. Then you ask 14. Then 14 said, well, actually I have 11, so here you are, right? So, but this is really not ideal, right? Because you have to ask in the order of all the server numbers. In this case, it's order of 5, right? So people come up with the cord protocol. Cord protocol is actually a protocol that's built on, as you can see, built on a consistent hashing ring, but instead of having a list of all the server, it has only partial list of all the server. Actually, it's has the log of n server items in the table, right? So actually, as you can see, there should be, or there could be, in total 8 servers, right? 8 is 2 to the power of 3. Therefore, you have only 3 items in here. So this, as you can see, means, because this is 0, so it says for data 1, it's held by 1. That's true, right? For data 2, it's held by node 3. That's true, right? Because we don't have 2 here, so that's 3. And for data 4, it's held by 0, which is itself, but you know. So as you can see, it has only 3 items here, right? Similarly for 1, but can you see the pattern? This one is this key plus, or this node plus 1 plus 2 plus 4. This one is node 0 plus 1 plus 2 plus 4. This one is node 3 plus 1 plus 2 plus 4. Alright, so if you have a ring of 16, then you have a table of 4, then should have your key plus 1 plus 2 plus 4 plus 8. Alright, that's the rule. And as you can see here, right, from this, 2 is taken care by 3. 3 is also held by 3. 5 is held by 0. Right? 3 is in here in 3's table. 4 is held by 0. 5 is held by 0. 7 is held by 0. Right? Which is true. And so each one maintains only log n of item of the whole ring, and they come up with a protocol for routing or for searching with only log n hops. You can get the exactly the node which is taking care of the data. So let's see how it is. Well, here the table looks a little bit different, but if you consider this as 2 to the power of 0, or sorry, 2 to the power of 1, how to say, 2 to the power of 1 minus 1, that's 1, this is 2, this is 4, get that? So here, right, let's see, so the first example is this red line. People come to node 1, ask for who has data 26 or data set 26. So 1 will see, well, how to say, 26 is even later than my last one or furthest one, so I will just ask the furthest one, which is 18 here, so it goes to here. Alright, so the one will ask 18 about where is 26, and 18 look up its table and it says, well, it actually starts from here. It says 5 you have 4, right? So this is 1 2 3 4 5, this one. Then I just say 4 you have 28, and 28 also is since 3, but 2 you have 20, so I should ask this guy, right? So it goes to 20. 20 to say, well, the second one, or also goes from here, but here to say 28, 28, 28. Oh, there's 21. I should ask him. Okay. 21 say, well, my first one is 28, meaning my next node is taken care of from myself 21, but I have 21, so from 22 to 28, he has it. So this one goes to this one. So this one actually, it has this 26, right? So let's see one more example. All right, so people come to 28 to ask for 12. All right, 28 is going to find its table where the largest node, or right, the largest node that's before that value. So in this case, it's 4. So it goes to 4. 4 is going to look for its table to see, I want to find the largest one that's before 12. In this case, this one, which is 9. So it goes to 9. 9, look at its table to see the largest one before 11. It's before 12 is 11, so I'm going to 11. And 11 says, well, my first one, which is my successor, has already 14, so he must have 12. So this one asks, 11 asks 14 to say, do you have 12? Then 14 says, I have. So as you can see, now we have a ring of how many? 32 nodes, right? But for each lookup, it's around, let's say, 1, 2, 3, 4. In this case, 1, 2, 3, 4. Around 4 steps. So it's in a, order of log n. So that's pretty much how you form a finger table, or they call it finger table, but I was just saying it's a routing table, all right? How you retrieve certain data due to your table. And another question is, how do you construct this table, or how do you update this table when there's a node get out? Let's now go to the paper. All right. So the paper lists the pseudocode, or probably the real code, but I would consider pseudocode of all its functionality. As you can see, it has only actually 6 questions. Let's see how it is. So first question is called find successor. That is, when you are given an ID, each one is able to tell, according to its table, who is the successor of that ID. And the function returns if this ID is between this node itself and its successor, then apparently its successor has this one. All right. If this is not the case, it will find the closest node that's before this ID, and it will let that node to call its function of find successor. All right, then that node, by the time of that, the ID will fall between this node and its successor. Then its successor is really, the one who should take care of this ID. And like we showed in our, the picture there, So this is basically you go through your finger table to compare and find the furthest, or we can say the largest, as you can see we're doing from the bottom of the table to the top of the table. Find the largest or furthest node that is before this ID. All right. And here is how do people, how to say, manage the joining and the leaving of this ring. All right. Initially, there have to be someone who just create this ring, and its initiation is very simple. It just get in and set itself set itself as its successor, because when you have only one node and you want to form a ring, actually your predecessor and your successor as yourself. All right, but it says its predecessor for now, for empty for now, but actually it will be updated real soon. And all the other node who join after that, you have to find someone who has already in the ring, right? Or the second one will just get the first one. So in that case, also initially it says its predecessor as empty. It says its successor to be its real successor. Then how can this newly joined node know its successor? It will ask who has already in the ring to say, please find my successor according to your finger table, right? That's it. And how does this to be executed or executed? Here, right? So this is the logic. And this function is to handle when a node joins in. All right. So what it does is it keep asking its successor's predecessor. Basically, to say, it will ask its next guy to say who is your predecessor, and if it finds the answer, it's not itself. All right. If it is self, or supposedly, or if stably, right, your successor's predecessor is yourself. But if it's not, it's something new, then actually that guy is sitting in between, should be sitting in between you and your successor. That's is because that guy just got in. Alright? In that case, you just set that guy to be your successor, and you let this guy know you are before him. Right? Let's see, when that guy is notified by you, then that guy will set its successor to be you. Remember, if that guy just joined in, then his predecessor is now, which is this case. Alright, so he will set you in. So this stabilized function is called periodically. Alright, so people just keep checking whether there's someone between me and my successor. And the other function is called fixed fingers. That is also a function that's called periodically to make sure its finger table is updated. Alright, so it's just keep calling this most important function, finding successor, to check, right? As you can see, well, in the table, right? Basically, it says the successor of 1 is 1, successor of 2 is 3, successor of 4 is 0. This one means successor of 2 is 3, successor of 3 is 3, successor of 5 is 0. So basically, it just shows the relationship of successor of certain key, and this one just keeps calling that function to make sure it gets the updated result. And this one is called check predecessor. That is basically you are calling your predecessor to see, are you still alive? If it's not, you will set it to null. That's because only if you set your predecessor to be null, then when someone notifies you to say, hey, I am your new predecessor, you are able to set him as your predecessor. All right. So do you got it? It's quite a simple idea, right? So that's how to say the pseudocode or the algorithm of this core protocol, and I implemented using several tools, right? So first of all, I'm using Node.js, and to write as my server or as my node, using Node.js as node, and for communicating between different code, I'm using the T channel from Uber. Right? Well, it's an open source by Uber, T channel, and it is basically a protocol for RPC, and it has it's also kind of library, so it has 4 versions for Node.js. I'm not gonna show it. Node.js, Python, and Go and Java. So you can choose whatever you like, just to use it. And besides that, I'm also using a tool called Hyperbarn. Yes, that's also a tool that's built by Uber that is for service discovery or routing. Well, in your solution, you can actually assume that everyone knows the IP address of everyone, so actually you don't have to do the service discovery. But that's just some useful thing that you can use. And besides that, so I'm gonna do a demo, and in the demo, I'm going to show the example actually introduced by the paper. Well, they have 2 version of paper. I'm going to show the simpler one. All right. So base case is this, right? Is we have only 3 nodes. That's 0, 1, and 3, and they should have a table of this. All right. So in 0's table should be 130, in 1's table should be 330, and 3's table should be 000. All right. So that's the initial state. Let's have that. All right. So I'm going to start this one. I have already Hyperbarn running actually, so that they can find each other. But I'm just gonna start those services, and I'm printing the finger table. As you can see, 130, 330, and 000. Right? That's 130, 330, 00. So what happens if there's some node join. All right, in this example, 6 joined. Then they have to update their table. See that? That used to be 130, but now it should be 136 because 4 is not held by 0 anymore. It's held by 6 because 6 joined. So it just takes over 4, 5, 6 from 0, remember? And the 1's table becomes 336. 3's table becomes 660, and 6 will have a table of 0, 3. Let's see whether that's true. Alright, so we have a 6. I call it node 6 join. But watch here, right? Watch here, the predecessor successor is updating slowly, and the value here also is stop updating. So as you can see, 136, 136, right? 336, 336, 660, this 660, 003, 003. Okay, this is an example of node join. Next example is to what if somebody left? What if somebody's gone? Right? So if 1 is gone, they have to update their table. Alright, let's see whether that's true. So that's 0, 1, 3. I'm just gonna queue this one. Alright, so now 1 is gone. As you can see, it's changing. See that? Okay, so actually, right, I remember that this is actually or you can say typo or mistake. So this one is saying 1 should be held by 0, but actually, as you can see, that's actually not that case. Actually, 1 and 2 should be held by 3, and 4 should be held by 6. So this should be 136, right? But this is a mistake in the paper. You're gonna see that. So it should be 136. And this one should be 660. Let's see, 660. This one should be 003. 003. This one, oh, that's why I just scrolled. Hold on, what's right? 336, right? We said should be 336. Okay, cool. So we got what is supposed to be, and that's pretty much it. So, and I also, gonna attach my GitHub, repository for my code. So just contact me if you're interested in discussing whatever, discussing the code, discussing the concept of DHT, or discussing the Uber's T channel or Hyperbarn. All right, thank you.